Hello, welcome to my channel. This is the 5th episode of the busy reaction video series, also known as the Belousov-Zhabotinsky reaction. This is one of the most intriguing, most visually striking, and most lifelike reactions where we can observe self-organized wave patterns or rhythmic patterns in a spontaneous chemical system. In one of the previous episodes, I left an open question. In this busy reaction, the waves appear to be much more curly. Make sure to stay until the end of the video to find out its secrets. Previously, we had talked about different variations of busy reactions. It can be catalyzed by each catalyst alone or a combination of them. A natural question to follow is that, can we use different substrates as well? In this paper, the author pointed out that, other than the acidified bromate solution, a wide variety of reducing agents and the transition metal containing catalysts can be used for busy reactions. On this channel, all previous experiments utilized the mannolic acid as the substrate, which isn't exactly an easy ingredient to obtain for amateur chemists. Before we investigate other substrates, let's examine the chemical structure of mannolic acid and understand why it's an ideal substrate for busy reactions. This leads to one of the most important concepts in organic chemistry, enols and tautomerization. You see, nature always prefers low-energy states. If two chemical structures have similar energy states, with identical atoms and their corresponding arrangements, except for one hydrogen atom, they can usually interconvert to each other easily. A prominent example is when two carbonyl groups are one atom apart from each other. Let's look at the chemical structure of mannolic acid. Because of its structure, the carbon-oxygen double bond can easily migrate to the adjacent carbon-carbon bond. To satisfy the octet rule, one hydrogen on the middle carbon will migrate to the oxygen on the top. This enables a hydrogen bond between this hydrogen and the adjacent oxygen, forming an enol structure with a stable six-membered ring. In the solution, these two structures coexist and they can readily interconvert to each other. While the original form has an sp3 hybridized carbon in the center, it generally resists reaction with bromine molecules unless high-energy UV was applied. The enol form, on the other hand, with a carbon-carbon double bond adjacent to a carbonyl group, is far more reactive and can easily react with bromine molecules to form a carbon-bromine bond. The chemical bonds here are not to scale, particularly the HBr. Due to the Le Chatelier principle, as the enol form was consumed, the reaction will move toward enol formation favorably. This completes the reaction 7 in the busy reaction mechanism elaborated in the last video, generating the bromide ions whose concentration is quintessential to the oscillation nature of this reaction. Consequently, in theory, chemicals with a carbonyl group adjacent to an alpha hydrogen can participate in the busy reaction, as long as no other functional groups can interfere with the reaction. Researchers at Florida State University successfully created the oscillating pattern using 1,4-cyclohexene dione. You are now witnessing the video of them creating self-organizing patterns using 1,4-cyclohexene dione. I'll put a link to their channel in the description below. In the meantime, many researchers reported that acetone can be used in this reaction as well. Acetone, being the simplest ketone, can be found in nail polish removers. In this video, let's find out if we can successfully recreate this reaction with acetone. First, let's review all the ingredients we have used so far. Here is a list of all of them. For acetone, I have obtained it from nail polish remover. I have prepared a petri dish with 7 ml of solution A, around 0.2 ml of acetone, 0.5 ml of solution C, and 1 ml of solution D. This is the same recipe used for previous petri dish experiments in this channel, except that mannolic acid was replaced by an arbitrary amount of acetone. You are now witnessing its reaction in a time-lapse video. Despite my best efforts, no visual change was observed. It could be explained by two factors. First, my acetone came from the nail polish remover from the grocery store and it may not be pure enough. Second, the chemical change is not visible to the naked eye but can be detected by some scientific equipment. Either way, acetone appears not to be a good substrate for homemade BZ reactions. Should we abandon our efforts? Not so fast. Given that the acetone-only version was unsuccessful, at least it did not produce the visual patterns as we expected. Could we make some modifications to make it work? The most straightforward way is to add both acetone and mannolic acid. So, in a separate experiment, I've made a petri dish with 7 ml of solution A, 1 ml of solution B, 0.2 ml of acetone, 0.5 ml of solution C, and 1 ml of solution D. After the solution becomes clear, my chemical instinct tells me that the acetone will consume a small amount of bromine, so I added an additional 2 ml of solution A, which is the sodium bromate. It should be noted that the reaction between acetone and bromine should be far slower than that between mannolic acid and bromine, so the mannolic acid should still be the main ingredients responsible for the BZ reaction if the reaction occurs at all. In this video, you are witnessing the reaction from a time-lapse video. To my great delight, this reaction indeed worked, and it generated a distinct pattern different from any previous experiments. This makes sense because the addition of acetone has changed the viscosity of the solution, creating a different environment for ion diffusion. I've repeated this experiment several times. Each time, a different pattern was created, but they are, in general, more curly than the previous patterns. Keep in mind that, despite my best effort, each round will have a small variation of concentrations among all ingredients. Similar to previous experiments, this reaction can be reset by gently shaking the petri dish, and a new round of oscillation would occur afterwards. The patterns generated by this one is by far my favorite. The pattern resembles the sun and the moon in the beginning, and as the waves propagate, it generated two wave fronts that eventually meet with each other. The video you have witnessed in an earlier episode consists of the BZ reaction with both mannolic acid and acetone. Instead of using ferroin as the only catalyst, it utilized both ferroin and cerium 4 ions as catalysts. Similarly, This reaction can be catalyzed by ferroin and manganese too. After generating intriguing patterns, the reaction mixture will form the brown manganese dioxide precipitate, which is characteristic of manganese-catalyzed busy reactions. We can even observe the propagation of waves of manganese dioxide particles. That concludes the video for today. Hope you had learned something new. It takes a lot of time and effort to make a video like this. If you are intrigued by this video, please feel free to like, subscribe, share, and comment so I can create more videos like this. See you next time!